I want to speak about the connection between conformal field theories and codes. Over here, I spoke about this topic in a virtual seminar here in May, and my collaborator, Al Shapir, he's not around, but he's visiting the institute. He spoke about the same topic in November. So therefore, my plan for today is the following. I want to speak about the more recent developments where we are trying to understand the meaning of this connection between codes and CFTs. So I would try to maybe first try to go through this old material, which you heard about already twice. I will try to go in a telegraphic way. Hopefully it will take me 20 minutes to do that. And during the rest of my talk, it will be split into two completely orthogonal directions. We were trying to understand the meaning of the codes, or if you wish, the value of that connection. And there are two different approaches. The bottom-up approach, which is more algebraic. It's mathematically sound, but there is no obvious role for the codes in the sense of equal to preserve information or quantum information or anything like that. And there is another approach we took when we were trying to map CFTs to quantum codes, such that we will have some information theoretic structure. But then again, it's not entirely clear if this is the final word and if the structure is absolutely, well, what's the value of that structure? So there will be two different things. And I'll just try to go quite fast in the first 20 minutes. But of course, if you have any questions, please stop me. Maybe I'll try to put archive numbers on the whiteboard in case you would have some questions or interest in this topic, and I'll try to see the details. So first, I'll speak about all papers we have written with Al Shapir, and these are the papers we already both talked about here. So I will start with the classical codes, classical linear binary codes. And these are linear spaces inside Z2 to the power n. So the element, so the linear space inside Z2 to the power n means that we have a bunch of binary strings of length n. Element of the string is either 0, 1. You can add those strings, you can subtract them, but it's the same as adding because all algebra is done mod 2. So the dimension of the code in this case would be 2 to the k. So you can think about this as a vector space, and it has k basis elements, and therefore the number of possible combinations is 2 to the k because there is only possibility to add them with to each other, make linear combinations with the coefficients 0 and 1. The simplest example would be the code which consists of two code words. A code word is just an element of a code. It's a binary string. There's always 0 code word because it's a vector space, and then there will be unique non-trivial one of this form. So in this case, k equal 1 and n equal 2. Okay, maybe I should take my notes because this way I'll understand better what I need to tell you about. Okay, so on top of this structure, we can introduce the scalar product. The scalar product will be introduced in a completely standard way. You have a vector, you multiply it by another vector, but in the end of the story, we will only take the answer mod 2, such that the scalar product could be equal to 0 or 1. Since the scalar product could be equal to only 0, 1, you can have something in this case, which cannot happen in the conventional case. You can have a vector which is self-orthogonal. For example, this vector C1, it's self-orthogonal because its scalar product with itself is 2 mod 2, it's 0. Okay, so once we introduce the scalar product, we can introduce the notion of a dual code, which is a vector space dual to this. A dual vector space is defined as a combination of all vectors, which are orthogonal to all vectors from there. Now, if a code is self-dual, if a vector space is self-dual, at the level of code, we call it a self-dual code. Self-dual code. Now, this is something which could never happen in the conventional linear algebra, but now it happens because everything is discrete. So for example, this code is self-doing. Okay, good. Now, another important characteristic of a classical code is called the spectrum. If we have a code, we can try to keep track of the size of these vectors, but we will define the size sort of the conventional way. We will introduce norm C, which is simply one norm. It's simply the number of non-zero elements, in which case it's the number of ones. Once we introduce the length of a vector, we can define the notion of the spectrum of the code as the information about lengths of all vectors inside the code. So to properly package this information, we can introduce what is called the numerator polynomial. And that's an auxiliary polynomial, which
C1 is the number of non-zero elements.
C1 is a norm, it's a one norm, so it's simply the sum of absolute values of the elements of the vector.
So this was the first thing you've done that wasn't invariant under automorphisms of the vector space.
What kind of automorphisms?
Vector space with dimension n has a group GLN.
Yeah, it's not, I don't think it's
everything until this point was invariant under GLN.
No, it's this notion of norm is not invariant. It's only invariant under permutations. Yes. Right. So the spectrum is only invariant under permutations. That will give rise to the notion of code equivalences when we permute elements of this vector. So you can think of each element here as a classical bit of information, which could be 0, 1. And then if we permute bits, everything should be invariant in a sense that we start with one code, we permute bits, we have another code which is called equivalent. That's the notion of code equivalences. Okay, so this auxiliary polynomial only knows about the spectrum, and it will be a sum over all code words, and then it will be n minus c, need for absolute value, and 1 to the power c. So I don't need to have here two variables. I put them such that this polynomial is homogeneous. Otherwise, it would depend only on one variable. And what this polynomial simply calculates in front of each power, y to the power c, the coefficient in front of each power is simply the number of vectors with a particular length. So this polynomial only knows about the length of the vector. It doesn't know the angle between vectors, if you wish. It's called the spectrum. Now, if the code is self-dual, the following algebraic identity holds. It's called, I think it's called McEwen's identity. And it means that the vector x and y, if we rotate it by a 2x2 Hadamard matrix, the polynomial doesn't change. Okay. So far, so good. Since you probably saw this recently, as recently as November, there is nothing new here. Let me go to the next chapter. I want to connect codes and lattices. There is a canonical way to start with a code of the kind I'm discussing here and define a lattice. I will be drawing two-dimensional lattice, but it should be n-dimensional, provided that my code, the length of the code is n. The recipe how to build a lattice from a code is very simple, and I'll try to describe it in a geometric way. First, we recognize that code words, there's a vector, binary vectors of length n, which means that each code word is a point, is a vertex on a unit cube. Obviously, not all vertices are used, but there's some vertices of unit cube. So first, we take all the code words and highlight them on the unit cube. And in this example, it will be 2 points. Okay, and then the next thing, so there could be a multi-dimensional cube. There will be a bunch of vertices highlighted on the unit cube. And then the next step we do, we take this, I can try to use color chart. Then we take this unit cell and we move it to left and right in all directions with the step 2. So in this case, this point will have a lot of different sort of avatars, this, and this, and this. And with step 2, there will be infinite number of those images of this point. Okay, and then also this point will also have a lot of these avatars. This, and this, and so on and so forth. And once I put all of these copies on this cubic lattice, I will see that those highlighted points, they form a sublattice of a cubic lattice. So my original lattice was cubic, but my resulting lattice is not cubic. It's a sublattice of a unit lattice. Excuse me, it's a sublattice of a cubic lattice. So in this case, the unit cell looks like this. It's not cubic. So that's a canonical way called construction A. We'll build a sublattice of a cubic lattice starting from the code. And for some technical notion, for some technical reason, I will shrink this lattice by square root of 2, such that this point, it used to have a coordinate 2, 0, 0, 0. Now it has a coordinate square root of 2, 0, 0, 0. That's this point. Okay. Now, with this kind of lattice, well, with any lattice, we can define lattice theta function. The lattice theta function is a function, is an auxiliary function which depends on an auxiliary variable tau. The only job it can do, it can store information about the spectrum of the lattice. Spectrum of the lattice means the lengths of lattice vectors. So these are all lattice vectors. I can calculate the conventional length of this vector from here to the origin, and lattice theta function is a vehicle which stores this information. Now, if I want to calculate the lattice theta function for this kind of lattice, I can do it in the following way. I need to sum over all highlighted points, but I will do it into 2 steps. I first calculate the sum over images of origin. And then as a next step, I will sum over all images of this non-trivial code word. Sorry, it should be highlighted. So it's clear that each code word, this is a trivial one, this is non-trivial one, gives rise to some kind of cubic structure. Mathematically, for example, mathematically, these orange points, they don't form a lattice, they form a periodic structure, which is akin to crystalline lattice, but mathematically it's not a lattice because it doesn't start with at the origin. But we can sum over all of these points, and it's very easy to see that the sum would be given by Jacobi theta functions to some power, because just Jacobi theta functions, they go through the cubic lattice and pick certain points. So the punchline here is the following: if I start with a code and define a lattice like that, then the lattice theta function associated with the code will be simply given by this enumerator polynomial, where 2 of these auxiliary variables x and y become the theta functions. Okay. All right. So that's basically what I need. Okay, I will be very frugal with space. Right. Okay. So the crucial thing here is the following. If I start with a self-dual code, which is defined here, and I build the lattice this way, the resulting lattice will be self-dual as a lattice, which means that all points, the scalar product will be an integer number, and moreover, the dual lattice will coincide with this lattice, which means that all vectors which have integer scalar product with these guys also belongs to the lattice. So that's important because if I also add an additional condition, right here as an additional condition, I can demand my code to be double even. Right? What does it mean that the code is double even? It means that the length of any vector C, any code word, is divisible by 4. If the code is double even, it's not difficult to see that in this case, this lattice will be also even. And it also easy to see that in this case, this polynomial W would satisfy very simple algebraic identity. I can multiply variable y by I. That's completely obvious from here because all C are divisible by 4. And therefore, if I multiply if I multiply variable y by imaginary I, then the polynomial will not change. So if I start with a double even self-dual code, my polynomial will satisfy these two identities. And my lattice will be even self-dual. And then I will be able to define a chiral CFT with help of this lattice. And then the partition function of this chiral CFT will be given by lattice theta function, which in this case becomes the polynomial. And then I will have the Dedekind function in the denominator. So that's pretty much all I wanted to say about classical codes. Maybe to conclude, an interesting question is to understand why this Z would be modular invariant. Now, it's actually a tricky situation in the chiral case because if C has to be divisible by 8 by construction, let me not explain from where that comes.
That just comes because otherwise you don't have a code that's double even.
Yeah, that's correct. That's correct. If one wants to satisfy both of these conditions, it's not entirely obvious, but it's only possible if n is divisible by 8. And then we all know that the denominator will not have proper modular properties unless C is divisible by 24. But this is an artifact of the chiral case, which will not be important for me because my main discussion will be about non-chiral CFTs. So let me just focus on the numerator. The numerator will have proper modular properties in this case. And those modular properties will come automatically from the properties of Jacobi theta functions, and importantly, the properties of the polynomial W. And these properties of polynomial W, they are here already at the level of the code. So this property will ensure proper transformation under tau goes tau plus 1. And this will ensure proper transformation under tau goes minus 1 over tau. Okay. So that's maybe all I wanted to say. Just to conclude, in principle, I don't need a code in this case. I can ask the question if I can find a polynomial which satisfies both of these properties. This is a mathematical question which has been answered. You can write down the all polynomials of that form as an arbitrary polynomial in terms of two specific polynomials. And then in principle, you don't even need the code, you don't even need the lattice. If you write something like that, you will have a modular invariant object. So let me switch to the quantum case. So I will really shift gears at this point because my discussion would be discontinuous. I will discuss quantum codes, which at first glance don't look like this at all. So let us mentally shift. I'm discussing n qubits. And then Hilbert space of those n qubits. And then I will say that code subspace is some subspace of Hilbert space of n qubits. And I want to define this code subspace with help of the following algebraic structure. I want to define an abelian group called the stabilizer group. And the elements of this group are the generators I will call GI, and GI, they commute with each other. And then they square to 1. So in disguise, I can think of them as Pauli matrices in some specific basis. So I can say that in some specific basis, these are Pauli matrices acting on a particular spin. They're all acting on different spin, therefore they commute, and they square to 1. Okay, very good. And then I'll say that this code subspace is defined as a space stabilized by my stabilizer group. That's why it's called the stabilizer group, because it doesn't act on the code subspace. I will discuss special kind of codes, self-dual codes. Which means that I will have maximal number of stabilizer generators. Right, it's a maximal number, it's equal to n. And then in this case, there is a unique psi, which is invariant under all stabilizer generators. It's unique up to complex number, which I can multiply. So you can think about this way. I have n qubits, you have n Pauli matrices sigma z, each acting on an individual qubit. And if you ask what are the states which are invariant under all of them, this is a unique state with all magnetization up. That's a unique state. And then you can apply some very large unitary transformation, then everything becomes murky, but there is a unique state which is invariant under all of them. Okay.
So first you wanted the code subspace, not a single state.
In this case, the code subspace consists of a single state. And this, strictly speaking, these codes cannot be called an error correcting codes. In the context of quantum computing, they should be called the error detecting codes. You have a unique state, which is in the code subspace. If your error moves you out of that space, then you can detect that error. So that's a proper interpretation of those codes in the quantum computing sense. Again, in the context of quantum computing, if you want to be able to detect that error, you should be able to apply this G to your quantum system and measure it. And therefore, we want this operator G to be simple in the computational basis. And people agreed that the following ansatz should suffice. You consider G, the generator of the stabilizer group, to be a product of 1 qubit gates. So U is a 2x2 unitary, which acts, it's a 1 unit, 1 qubit gate. It's a 2x2 unitary, acts on a particular spin. And then we don't even have to consider most general unitaries. We can consider only U to be equal identity or one of the 3 Pauli matrices. Okay, and therefore it means that the corresponding GI, it can be, I don't need to write indices because it's clear with these notations that each U is acting on a particular qubit. And then we can parameterize those U by indices alpha. And index alpha could be either 1, X, Y, or Z. So it has 4 elements. There is a elegant mathematical way to say that alpha, which is an index which can take 4 elements, has to be an element in the field F4, and field F4 has certain algebraic properties. Okay, so this is basically the way how quantum codes work. And one way to formulate quantum codes, quantum stabilizer codes, is to say that these are codes over F4 with a particular scalar product. But this is not the notations I would prefer to use. So I would prefer to say that instead of having a product of Pauli matrices like this, I want to write it as a product of X and Z Pauli matrices. And then each A could be either 0 or 1, and each B could be 0 or 1. And of course, if I have 0, 1 here, 0, 1 here, 2 by 2 is equal to 4. So with these 2 binary variables, I'm storing exactly as much information as I'm storing here with one variable, which is in F4. And with these notations, I can say that a generator of my stabilizer group is parameterized by a vector AI and BI, where A and B both belong to Z2, these are binary strings of length m, which means that this long binary string belongs to Z2 to the power 2n. Okay, so what I did here is rather standard. There is an isomorphism with respect to certain algebraic properties between F4 and Z2 cross Z2, and that's what I used to write an element in F4 as 2 elements in Z2 cross Z2. But in a more simple way, I have written my generator of a stabilizer code as a binary string. And once it's a binary string, then it's already kind of similar to the classical codes. And now we'll try to make this similarity explicit. Okay, so to make this similarity explicit, I should say that all generators commute. That simply follows automatically because at the level of these vectors, that will be an addition operation, and addition is a commutative operation. But that's not entirely true. There actually will be a constraint, and constraint will be of the following form: AI multiplied by bj minus aj multiplied by bi mod 2 should be equal to 0. That's a constraint which my generators should satisfy. At this point, this generators G, which I parameterize by binary strings, I can just forget about generators, just think about binary strings. I can call them code words, and I say that I have a bunch of code words, and they should satisfy this identity. So basically, at this point, I reformulated my quantum code as a classical binary code, which satisfies certain identity. This identity could be understood as a self-duality identity with this kind of metric, but this is not really a metric. This is a symplectic product, right? You see it with the minus, it's a symplectic product.
But you're working mod 2.
I'm working mod 2.
So it doesn't matter.
Oh, that's right. That's right. But let me continue on my course. If you were to generalize this story from binary qubits, these are binary qubits, right? You can generalize that to qubits. You can do that quite straightforwardly. And in this case, everything will go exactly the same way. Here, instead of X and Z, you would have what is called shift and clock matrices. A and B will be elements not of Z2, but of ZD cross ZD. And here I will have something like mod D. And here I will truly have a symplectic code. So let me reiterate. There is a completely standard way how you start with the quantum code acting on qubits, and you end up with the classical binary code. Excuse me, it's classical, it's not binary. It's a classical code with elements being letters from ZD, and then there is certain symplectic product structure. Okay. But as Ed said, in D equal 2 case, it's a special case. Let me go back to binary code. In that case, minus and plus are equivalent, and that's very important for me because I put plus here, and my symplectic product becomes the conventional scalar product, and it looks like this. And this is exactly the scalar product in the space, in the Euclidean space, in the Lorentzian space with the signature 1,1. Okay, so but this is a special case for binary codes. Any questions about this? Let me maybe erase this starting from qubits. I'll forget about qubits. I'll simply think about my quantum code as a classical code with this scalar product, with this finite scalar product, which is a scalar product in Lorentzian space. And the rest follows quite straightforwardly. I can define self-dual code. In this case, my enumerator polynomial will consist of 4 variables. There will be 4 variables because my enumerator polynomial, so C is a binary string which consists of A and B. So this C, elements of C could be letters which have 4 possible values, 0, X, Y, and Z. So therefore, I need to have different variables, 4 different variables. It's a homogeneous polynomial of 4 variables. This is what is called the weight. This is a number of X in my code word. This is a number of Y. This is a number of Z. This is a number of zeros. And I have a homogeneous polynomial of 4 variables. If my code is self-dual, it means that W of T, X, Y, Z is equal to some transformation here. And this transformation works in the following way. You take this vector and you multiply by 4 Hadamard matrix. So it's quite similar to this transformation here. Here it was 2 by 2 Hadamard. Here it's a 4 by 4 Hadamard. You impose additional condition, which is evenness. Well, in this case, it's like evenness, but it actually should be regarded as a reality condition. And in this case, it's simply an ability to flip the sign of y. And then let me remove this definition. Once you have a code which satisfies both of these conditions, you can define a lattice exactly in the way how described there, but the corresponding scalar product of the lattice will be this one. So it will be an even self-dual lattice in the Minkowskian space. Corresponding lattice will be even self-dual lattice in the Minkowskian space with the signature n, n. You can define an Narain CFT with this lattice. You can calculate the theta function. Theta function will be given by the polynomial, and the CFT partition function will be given by W. And then instead of T, X, Y, and Z, you will have certain combinations of the form. It will be certain combinations of the Jacobi theta functions, which I don't want to write explicitly because we will not use them. But the idea is the same. You can write the CFT partition function explicitly through only code information. There is a polynomial, it satisfies two algebraic identities. This identity makes sure that the numerator behaves covariantly under tau goes into minus 1 over tau. Actually, this is just opposite. This corresponds to tau into tau plus 1, and this corresponds to tau into minus 1 over tau. I'm going out of time. Any questions about this? So this is an old story, which I already spoke about. Maybe I'll try to conclude something here. So what is nice about this? It's nice that we can describe some Narain theories very explicitly and write the partition function just in terms of a polynomial. Polynomial would be a much simpler object to deal with than the whole Z. And then maybe we can do something interesting with this ansatz. You can think about this as an ansatz to solve modular bootstrap equations, because once you have a polynomial which satisfies both of these identities, you can easily write Z, which satisfies all necessary constraints of the modular bootstrap. Okay. So one application we had like in our original papers was the following. We were able to write a bunch of these polynomials which do not correspond to any code at all. And then it would be ZCFT, but there is no obvious CFT for those Z. And we were trying to understand if corresponding functions we have written, if they're actually partition functions of any CFT at all. So we conjectured that those functions probably don't correspond to any CFT at all. And we worked on that. We were able to show there are 6 functions like that we have written. It's for n equal 3. There are 6 particular polynomials which satisfy these properties, all the positivity, all coefficients are integer positive. So we have 6 functions which are satisfying modular bootstrap constraint, but not naively coming from any CFT. So we were trying to understand if there is a CFT for those functions. We have proved already that there is no Narain CFT, which gives rise to those functions. And for 4 out of 6 functions, we have proven after some work that there are no CFTs at all. But the proof is case by case based. So we are analyzing the corresponding spectrum. We try to analyze what could be the Carl algebra for the corresponding Z. And then we try to see if we can combine those Carl algebra characters in a modular invariant way. And if we conclude that we cannot, then we say that there is no corresponding CFT. So this is a proof which is very difficult to generalize, but it gives you explicit examples of functions for which no CFT exists. But otherwise, if you look at them, they look completely healthy. So that was first application. But then,
so the point is to generate some modular invariant partition function,
yes,
which does not have a CFT.
Well, that was one of the applications. Yes, that was one of, and naively it would satisfy all properties, including integrality and positivity of all coefficients. Yes. Okay, but then another application which we had in mind is the following. So now I will start speaking about more recent stuff. At some point, we observed, well, we can ask the standard question for the modular bootstrap. If you fix the central charge, what could be the largest spectral gap for that value of central charge? And that question can be asked specifically for the family of Narain theories. We know that this question is very important in the context of very large central charge when the theory has just Virasoro symmetry, because we expect that large spectral gap theories would be holographic and we want to understand them. But just to get some experience, we can ask this question for Narain theories. We can discuss separately if we expect those theories to be holographic or not. We actually discussed that in this paper. But as an exercise, I don't have to strongly motivate that. We can just say, okay, what if my n is equal to 1, 2, 3, 4, and so on? These are von Narain theories, so central charge is integer, and then we want to maximize the spectral gap. This question was addressed numerically in a paper by Nima and collaborators. And then we saw, by looking at the result, that for n equal 3, 4, and 5, the theories they identified as the theories with the largest spectral gap, as the Narain theories with the largest spectral gap. And I'm talking about the spectral gap of U1 to the n primaries. We saw that these are the code theories of the kind I just introduced in my previous slide, if you wish. And then we thought, okay, maybe this correspondence to code could be good for constructing theories with the largest possible spectral gap. Now, we saw in their paper that for n equals 6, the corresponding Narain theory is based on the lattice, which is a famous Coxeter-Todd lattice. And that lattice is known to be related to hexacode, which is a code over F4. So it was clear for us that this theory is also related to codes. And we were able to actually extend our construction, which I explained before. We were able to extend it in this paper and show that those two theories are also code theories in a sense that there is a way to construct them starting from the codes by extending our construction. So good. So then, of course, you want to ask what about 8, 9, and so on and so forth. For 8, we know, again, from the paper by Nima Khadijadi and his collaborators, that this is a very special lattice, which most certainly has relation to codes, although we haven't worked it out. But then you also want to ask the question, what if I go n goes to infinity? Can I hope that my theories, which I would call optimal theories, these are the theories with large central, with large spectral gap, is there any hope for those theories to be related to codes? If there is a hope, that would be interesting because we don't really have a good practical way to construct such theories. Maybe with codes we'll have better luck. So that was the motivation. And I already erased the lattice which was here, but let me very quickly restore that lattice. So remember how I built my lattice starting from the code. I had the point at the origin and I put it in a parallel fashion here, and the coordinate was just this one. And the length between this point and this point, the length squared, is just 2. Which means that it doesn't matter what kind of code I consider. It doesn't matter what kind of code I consider. This point is always here because it's an avatar of the origin. And that means that it doesn't matter what kind of code I have, corresponding Narain CFT would always have spectral gap smaller than 1. In a sense, we were lucky that for these two theories, spectral gap is exactly equal to 1. And therefore, our construction works. But that's a fundamental limitation of our construction, because we understand that as central charge increases, spectral gap also has to increase, and there is no way to keep track of, there is no way to use that construction to reproduce all those things. So here we need a completely different construction to increase the size of the spectral gap. If we ever hope to go down to infinity, we cannot get around with just one construction. We need a series of different constructions for each n, for larger and larger n, we need a different construction, which presumably would give you a CFT with a large spectral gap through codes. So we were trying to build some series of constructions.
Are these current CFTs or non?
No, these are Narain CFTs. These are not Narain CFTs.
Okay.
No, non-chiral.
Okay.
These are Narain CFTs. But the problem is exactly the same. And the picture applies to chiral lattices, to lattices in Euclidean space, but the problem is exactly the same in the non-chiral cases as well. So I will try to spend next 10 minutes to give you some idea of this construction we have. It's an unpublished work in progress, but I think we have some interesting results which I want to share. And the construction is very straightforward. We can consider first two-dimensional space, and lattice is a lattice in two-dimensional space, something like this. And this is our metric. This is a metric in a Lorentzian space. And we want to define a dual lattice, which is something like L-1 transpose. And then we want the lattice to be integral, which means that our original lattice is a sublattice of a dual lattice. Okay, and then we can consider a quotient. We can consider a quotient. This algebraically, that would be a finite abelian group, but that simply means that we have a finite dimensional torus, two-dimensional torus. So this will be something algebraically ZA cross ZB, a finite number of elements. But then the idea here, this group will be a sort of it will be our alphabet, and we will construct code. So we will construct code from the letters in this alphabet. And each A is an L, it's very bad that I'm using A for everything here. D1, D2. A will be elements in this alphabet. Maybe even better, I will say that pair A and B will be like it was before. In the example which we discussed before, D1 was equal to D2 was equal to 2. So that will be my code. I can understand it as a classical code where each guy A and B is a integer number from 0 to D minus 1, or I can understand it as elements of this abelian group. I will also inherit scalar product from this Lorentzian space. And the important thing here is that the scalar product which I inherit from the Lorentzian space, it will be a symmetric scalar product. It will not be symplectic, it will be symmetric, because the scalar product in my Lorentzian space was symmetric. So what does it mean? It means that I'm proposing some algebraic construction which looks like a code, but these are not quantum codes which you will get from quantum computing. Codes from quantum computing, this is symplectic codes. It goes back to your question. These are symplectic codes, and codes which I devise here, they are not symplectic codes. They have scalar product, which is a conventional scalar product, symmetric one. So these are, that's why I removed quantum from the title of my talk, because it would be unfair to call these codes quantum. Okay, but nevertheless, these are some algebraic structures which are codes, and I can play with them. And then very schematically, the idea is that you can, of course, define the numerator polynomial, and then you will have a lot of variables here. And each variable, it will be D1 cross D2 possible variables. So it will be a polynomial of many variables, but you can still define algebraic identities. There will be 2 of them, which you need to satisfy for the code to be self-dual and even. And that would assure that your corresponding lattice, I'll explain in a second how we define the lattice, but your corresponding lattice would be even self-dual in the Lorentzian sense, and then your CFT partition function will be modular invariant. Okay.
I just forget about codes and I think about lattices, right? So
Yeah.
in the Narain thing, you have some proper lattice, and here you're having a different kind of lattice where there are some.
These are Narain lattices. These are still Narain lattices. It's just that certain family of Narain lattices I parameterize by some algebraic structure, which I call a code.
Okay.
And a code is a collection of strings, with each element being an element of this abelian group. They're additive. I can sum them, and everything is understood mod D1 and mod D2 and stuff like that.
There's a special point in.
These are special points, and you already asked me this question in May. So let me go back to the question Juan asked me in May. I will first explain the question, then I'll give you. Juan asked the following question in May. That corresponds to the previous slide. Can I explain in simple terms what are the Narain theories I described with codes? Actually, I know the answer. The answer is very simple. In the binary case, it means that I'm compactifying my scalar fields on a cube of size 1 over the square root of 2. And I have some sort of integer B field. So B field, we know that B field is an antisymmetric matrix, but if you can consider B mod 2, it will be a symmetric matrix, because in this particular case, Bij only allowed to be 0 and plus minus 1. And then the B field, understood this way, will be a symmetric matrix. And then on the diagonal, we will have 0 because it started from being B field, which is an antisymmetric matrix. So the original construction discusses compactification on a unit cube. And you see that this cube is not very large, and therefore excitations of a Laplacian, they cannot be highly energetic. And that's the physical reason why I cannot have large spectral gap. With this construction, let me actually consider a very simple case where these two D are the same, and this D is prime. And then in this language, I can consider this to be a cube of size 1 over square root of D. So it's a very, very, very small cube. If D is very, very large, it's a very, very small cube. And then my B field will be defined mod D. And then it will be, Bij will be 0, 1, D minus 1. And then it will be symmetric matrix modulo D. Okay. So the torus of a Narain compactification is a cube, and the B field is a symmetric matrix. Well, it's a symmetric matrix mod 2 with an elements, integer elements. And 0 and D are T-dual. So 0 and D are equivalent because of T-duality. And then the following thing happens here. I can say that if D is very, very large, I have to start concluding. If D is very, very large, I have a very, very small cube. So the excitations over the Laplacian will be highly energetic. So the momenta of my scalar field will be highly energetic. That's good because I want to have large spectral gap. I want to have all states to be very, very energetic. But of course, there will be windings, and my cube is very small. And how can I make those highly energetic? So here I will hope that if I put some B field of special kind, this B field will preclude my windings to be light, because B field is coupling to my windings, and there is a chance for these windings to be energetic. And I will now try to argue that this is exactly the case. It's in the language of codes, it means that I'm considering a code of a particular kind, and I'm looking for the code, what is called Hamming distance, which means that I'm looking at the code word of the shortest length, and the length is defined as sort of, in the binary case, it would be simply the number of non-zero elements. But in this case, there are different elements of different kind, and each element weights differently, because each element here, when it becomes a lattice, would correspond to different geometry. So I need to sort of weight this code word in a particular way with a particular metric, and then I will try to find the code word with the shortest length, okay? Now, this is a problem which is very difficult to solve. People don't know how, even for binary codes, to find a code with very small. People don't know how to find a code with a very large shortest vector. That's a problem which is common for lattices and for codes. People don't know how to do it, but there is a very standard trick. In the case of codes or in the case of lattices, you can average over the space of all of them and see what the average result is. And then you can also argue quite rigorously that variance of that result is very small, actually exponentially small. And therefore, if you choose a random code or a random lattice, then the corresponding lattice, corresponding random code would have all the same properties as the average result. Okay, so what we were able to do in this particular case, we were able to calculate this enumerator polynomial. Oh, maybe I'm overselling this a little bit. I should say maybe just a little bit more accurately. We have a conjecture for the value of this enumerator polynomial, averaged over all codes of this kind. We have an explicit expression which satisfies all necessary algebraic identities, and we can check it using Mathematica for small sizes, relatively small sizes, that this is a correct answer. So that's our conjecture for the average polynomial. Once we have average polynomial, it knows information about the spectrum. It knows what kind of lengths of our code words we have. We can transform that into a polynomial of just one variable, such that something like this, where L squared will be literally the length of my vector in the conventional sense, in the conventional geometric sense. And that's when I go to the lattice, I will have these vectors of length L squared. And the standard L squared, the standard form of L squared and SL, it works like this. It starts with some exponentially small values, and then it very quickly grows, very quickly exponentially grows. And whenever this quantity becomes a order 1, that's when I have my, that's essentially this SL is a probability in a random code to have, it's a probability in a random code to have a code word with the length L squared. So if I take this probability to be 1, that's exactly the probability where, that's exactly the value of the length where I will find a vector like that in essentially all codes. Shall I repeat this? Was it clear? No, it was not clear. For the sake of time, let me skip. I think I did not explain this very well, but let me skip and just give you the result. The result here is the following. With this average polynomial, we can actually calculate the spectral gap of a random code, which means that we generate a random code, we construct a Narain CFT with help of that code, and then we calculate the spectrum gap of that Narain CFT. And it happens to be exactly at the level of delta is equal to C over 2 pi E. And we know that this is exactly the spectral gap of an average Narain CFT. So what it means is something like this. What it means is something like this. We have a full Narain moduli space. We can try to average over the whole Narain moduli space, and we can ask, what's the average value of the spectral gap in this case? And it is known to be C over 2 pi E. It's an average value. And then we have a construction with codes, and for given n, there is only a finite number of codes. It could be exponentially many, but it's a finite number. So we don't hope this set to be a dense set in the Narain moduli space. It cannot be dense. And I hesitate to say where it sits. Since I only start with a cube here, I would think that it sits only in a particular corner. I cannot know where exactly. But if I average just over this discrete set, I will get exactly the same average spectral gap. Okay, I get exactly the same average spectral gap. So this is good. And then the corresponding D, it has to scale linearly with n. So when I increase my central charge, I should simultaneously shrink my cube. I should simultaneously change this D. So this is the idea that if I want to have large spectral gap theories for large central charge, I need to constantly adjust my construction. I should constantly change my code. And my code was a code over ZT cross ZT. And I should constantly change this D. Okay, so what does this mean? It means a few things. It means that we managed to construct Narain CFTs in an implicit way, but more explicit than before, because their partition function will be given by some polynomial, and we can even calculate this average polynomial. And this psi AB will be some generalizations of Jacobi theta functions, which we can also write quite explicitly. These partition functions would have large spectral gap. We separately, in a paper a year ago, conjectured that this value of spectral gap is asymptotically tight. It's an average value. It's an average value, but we conjectured that it is also the maximal value. Now, this might sound like a strange thing to conjecture, because for average to be also the maximal, you need the whole distribution to collapse. But that's what we expect to happen. Of course, we don't have a rigorous proof. We only check that the variance is exponentially small, but the conjectures, similar conjectures, that an average value also becomes asymptotically largest value, such conjectures exist for codes and for lattice sphere packings. So in that sense, we simply generalized those hypotheses to the case of CFTs. And then we reproduce this conjecturally larger spectral gap from codes, which means that we implicitly conjecture that for these codes, the average value of the spectral gap is also the maximal one. Again, we don't have a proof, but that goes along with similar conjectures for other types of codes. I think that might be all I wanted to say at this point about this story. Maybe I should take any questions at this point. Okay.
I have a quick question. So can you go back to your B field intuition and show why it does what you said it would?
It's
directly from this picture, I mean, somehow?
It's a good question. So algebraically, it means the following. Yeah, so I should probably say that I promised to have two different stories. I didn't touch the second story. This was just the first one. Now, what Nima asked can be formulated in the following way. We can reformulate the code quite often in the following form. The code words, all code words, will be given by the matrix 1b. This is an n cross 2n matrix, and vector c is like length of this vector is 2n. And here you will have any vector of length n. Okay. And then you generate all vectors of this kind with a B, which is perhaps a random matrix of the kind we discussed. So it could be B transpose is equal to B mod D and BII equal to 0, but otherwise it's a random matrix. So that defines a code. This is called code generated matrix. And then the question is, you have all of these code words that there will be like d to the n of them, because all elements here could be any number between 0 and d minus 1. There will be d to the n of them. And then we want to go through all of them and find the shortest where length is defined in a particular way such that it will correspond to, in the binary case, it's just the conventional length, but in a high dimensional case, it should be some weights, which I don't want to write. Can I explain in simple ways why if this is a random matrix, it will give you an effective sort of length? No, but can I check it on a computer? That I can do. I can, for sufficiently small n and d, I can just put it on a computer and check whether, but essentially the question is the following. We have a conjecture for the average polynomial. Can we try to check it numerically on a computer for small n and d? That's exactly how we found it in the first place. So in that sense, this is like a self-fulfilling prophecy. But I don't know any simple way to explain why, if this is a random thing, it will be, you will never be able to construct a short vector. Maybe just to add one thing, you can do a naive thing. You can simply say, if these are random things here, and you can have like a length of one of those vectors, what it is. Then you can calculate and see that it is rather large. The tricky question is why you cannot combine those vectors in some particular way such that it will be mysterious constellations and you will have very short vector. That is, of course, nobody knows how to prove, but statistically we know that once you average, that will be the answer for the random one. So basically, something very simple happens. No miracle happens. And usually you cannot have a constellation which will create a very short vector.
For the case of the codes that led to partition functions that look totally consistent on the torus but weren't associated with any known Narain CFT. Well, first of all, can you associate any object in the world of codes with higher genus partition functions? And secondly, can you rule them out using higher genus consistency on higher genus?
The answer for the first question is yes. There was a paper by my student Ashish Kakar with his collaborators to consider genus 2. To consider ZCFT and a genus 2, you need to generalize the notion of the enumerator polynomial. It now will have a lot of different variables, but basically, if in my case it was a sum over code words, in this case you need to sum over pairs of code words, and what you write here will depend on the pair. So you can, right? So that's for genus 2. For genus 3, you need to sum over triples of code words and so on and so forth. So that you can do. Second thing, can you try to sort of exclude some CFTs? Yes, you can. And they had a paper about chiral case, and I know that they are planning to publish a paper about non-chiral case. I think excluding just one of those polynomials. So you basically you can make a progress, but it's not very strong. And it's only for Narain CFT in the end of the story. They needed some structure like that, I think. And yeah. In this binary case, all deltas are integer numbers divided by 4. So in our proof, we use that to argue that if there is a Narain CFT, corresponding Narain lattice would have certain mathematical properties. And then for n equals 3, we literally build all of those lattices. And then I don't know how many of them, because you usually build lattices and they're equivalent. So in some way there could be like 5 million lattices, but that's before the equivalences. But then we were able to identify all candidates and then show that none of them actually works. So for Narain CFT, there is a way to show that no Narain CFT matches that particular Z. But then if you want to exclude non-Narain CFTs, then you have to act on a case-by-case basis.
May I ask a question, please? Thanks for the talk. Thank you. Can you say a word about why the average versions of the numerator polynomials are also modular? Do they satisfy the 2 identities as well?
Oh, that's very simple, because let's look at the classical codes. You need to satisfy 2 identities, but both identities are linear identities. So if you start averaging over codes, you simply have a bunch of objects like that, which you arithmetically average over. And of course, this is a linear property, so it continues to be satisfied.
Thank you.
Any other questions for Anatoly? All right, if not, I remind you, we'll be getting together in the lobby at 6:30 to go to dinner, and let's thank Anatoly again for a wonderful time.